Now that we've got a very good guess, right, and understood qualitatively the behavior of this circuit as controlled by our governing equation derived from Kirchhoff's laws, let's actually try to solve this equation directly. Now, once again, we have a differential equation that we want to solve. This actually has the form of a separable differential equation. We're going to use the same techniques that we had discussed earlier for solving capacitor equations. In particular, we're going to use separation of variables. And you will recall that the strategy for that is to take all of the unknown parts, that's this current that we're trying to solve for, and get those all on one side of the equation, and then take whatever known parts are left over and move them to the other side. And you see the way we can do that, right? If we divide both sides by E minus IR, we will then have DI divided by that quantity, which is a nice combination for us because actually at that point we have just currents I on this side of the equation. And then we can move the other pieces that we understand to the other side by multiplying both sides by dt. And if we like, we can simply bring the current L over to that other side of that equation as well. So let's try to do that then. So I'm going to take this equation here, divide through by the right-hand side. What that will leave me on the left-hand side is di divided by the term I was dividing by, E minus IR. And then I'll leave a little space because I'm going to be doing some kind of integrations here. So I had brought this here to be under my I. dt goes up on top when I multiply both sides. And when L comes over to that side, it of course gets divided. So then that will equal dt divided by L. And we know that these little increments on both sides of this equation will always be exactly equal. And so then will be their sums if I were to add up all of those increments. So we can equate these two integrals. And finally, we have to keep in mind as we perform these definite integrations what the limits of integration are. In this case, we're integrating with respect to the current I, and we know the current started with value 0, so we're going to be integrating from 0. And then whatever we get to at the final point in our addition will just be whatever the current I is going to be at time t. That's my upper limit of integration. On this side, we're starting at time t equals 0 and adding everything up until time t, which I will call t. And of course, just to keep the mathematicians happy, remember your integration variable has to be given a slightly different name. So technically speaking, if you want to be technical, I should call this dt prime. Very good. Now we have a direct integration problem for us to try to solve. On the left-hand side, this looks like a logarithm, right? We've got 1 over something, so our best guess for that integral would be that it is the logarithm of the given quantity, E minus IR. And if I were to take the derivative of this, I would indeed get 1 over E minus IR. But because I'm taking the derivative with respect to current, right, because I was integrating with respect to current, when I do that, I get an additional factor that I don't want, which is minus R is going to come out. So to cancel that out, what I should do is multiply by minus 1 over R. So then the derivative of this quantity actually is the quantity that I'm integrating. Finally, on this side, we should not forget we need our limits of integration, which then would be evaluated between 0 and whatever the current is going to be at time t. In terms of the right-hand side of this equation, I just have a constant 1 over L times the integral of dt prime. So the integral of that is just t prime divided by L. And again, integrated between 0 and time t. And this side here is maybe a little silly, but substituting in t and 0, I'll get t over L minus 0 over L. And of course, 0 over L is just 0, so we don't have to worry about that particular term. Now, for this side of the equation, we can then substitute in I and 0. So then what we will find in this case is that we have the first term that we end up with is going to give me a minus 1 over r. The first term you see that we will get when I substitute in I is going to be the log of e minus I at time t times r, I of tr. And then we also have to subtract off the logarithm when we substitute in 0. So that will give me the log of e. And then the difference between these two, of course, has to equal t over L. And now you can solve this. Basically, we can almost do this here in our head, right? We multiply through by minus r and exponentiate. And then when we do that, what we are going to end up with is the following. On this side of the equation, we're going to have multiply by minus r and exponentiate is going to give me e to the minus r over L times time t. Then we're just exponentiating this piece, which will give me e to this divided by e to this power. So I'm just going to have this divided by the EMF. Multiplying by the EMF, I can put EMF here. And then what was left on this side was the EMF minus I of t times r. And then finally, we can rearrange this and solve for the current I. What we do is we move IR to this other side of the equation, move this term to the left side of the equation, and what we end up with then is E minus E times this exponential. So that means 1 minus E to the minus R over L times time t. And then that equals what we had left on to the right-hand side was I times R, and I can, of course, just divide by R then in order to obtain the current I at any particular time t. And that then gives me my solution mathematically. And then we can check out a few things just to make sure this has the correct behavior. Note that for t goes to 0, what I find is I get e to the 0, which is 1. So then I have e over r times 1 minus 1. And that gives me 0 for my current. And that's what we had said, right? We had said that that had to be a continuous function. And then when time goes to infinity, what we end up with is e over r as our current times 1 minus e to the minus infinity is just 0 in that case. So we see that e over r is our current as we go to, this was current at 0, and this is our current as we go to infinity, which is just what we would expect if the inductor just happened to be just a very simple wire. So our guesses actually turned out precisely correct, and once again then we can earn ourselves a nice happy professor symbol. It seems as though our solution worked out properly.